Hi everyone. What do we see here? We see here bars. They all are similar. They all are almost identical, but yet different. And to see the difference, one has to study them individually. Welcome to a new Cube video. And in this video, I demonstrate you another CubeGUI plugin, which allows you to study individual iterations of a loop. And this plugin is called Barplot. Let's do it. Hello everyone, and back to our video, to our terminal. And in this video I present you another plugin which allows you to study performance evolution of performance of a loop. Basically you could take a look, to closer look how the performance data changes from iteration to iteration. How to instrument and how to obtain such measurement I have demonstrated already in previous videos. Take a look in the collection. I also have presented you another plugin heat map which visualizes performance data of a loop as a 2D heat map with one axis the system locations, so basically all threads of the measurement, and another axis iterations of a loop. And one could go explore then which location, for example, takes more time in loop, or opposite, whether the some specific iteration suddenly takes larger time across the whole system tree, and so on. And in this plugin, it visualizes pretty much very same data as a heat map, just it displays it in aggregated form and offers a little bit different view. But before we proceed, I remind you to subscribe, to give us a like, and if you have any questions, to write them in comments. So okay, we start our instance of cube, and we open an example of a cube file which has a instrumented loop, for example this one. So this is a profile cubic, so it means it is a raw measurement of score P. So we measured visits, time metric, and some bytes sent and received. And we see that the main consists out of initialization phase, then some matrix data initialization, then Jacobi algorithm, and in the end the error checking, printing results, and finish. And our loop is actually inside of the Jacobi calculation. So, and our plugin which we would like to present, Barplot, is located here in system tree view, and currently it states there is no data to display, because to visualize any data one has to select the loop in its aggregated form. But before we proceed with that, we take a closer look how one can maybe configure this plugin. So for that one has to go into plugins menu, and one sees that here is a menu item system Barplot and Barplot settings. So in this coloring scheme it is hard to see, but that is the menu Barplot settings. And if we select here, we can see that we can customize basically how one displays the bar plot, the ticks, major ticks, minor ticks, the values where it is written, and the ruler, also iteration rule customization. It's basically to optimize a little bit with how the graph is visualized, but the principle of visualization stays then the same. So okay, in the case if bar plot is not listed here, it's not activated, it might mean that the application doesn't have the loop instrumented. So for that one has to go and redo measurement, or one has to assign some call tree of your interest and explicitly set it's a loop. what will proceed I explained in previous videos of where I show how the instrumentation of a loop is going on. So here I will not go into these details. Also, if in the case some error, initialization error happens, one can take a look here in this messages window and see if the plugin has been activated or not. So for example, here one can see it has been found first of all, and no errors happen, so it means it is available for this measurement. As well, one can take a look here in initial activation settings and click, and then one can see that here a system bar plot is listed and it is activated for this measurement. If this measurement doesn't have a loop, there will be no check mark. Okay, so now back to the actual plugin. So we have no data to display. How to have here some data? One has to go actually to the loop. So we expand, we see that there is a main loop, and as soon as we click the select loop, the plugin detects it and immediately visualizes the selected metric. So in our case, it's metric time, and it displays the metric time of every iterations, and we see that we have from 0 iterations up to 1000 iterations the metric time. So we have here 3 graphs: blue, lila, and red. So what does it mean? The blue graph, it's so-called maximal value of a metric for given iteration, like for example 47, and its maximal value in system tree. So if I select for example this iteration and I see that the value is 0.09, it means this value has been assigned, or it is assigned to some of the threads. In our measurement we have 16 threads, so we have 4 ranks and 4 OpenMP threads each MPI rank. So here this value has been assigned to some of the threads. We don't know which one, most likely the sum of the master threads. This line, or this color, the red color, that's so-called minimal value. So that is basically the smallest value along the system tree. And if we take a look from where is the same iteration, so it will be then 0.036. And lila, that would be the average value, so across the system tree. So in this case, we see that majority of the values are actually in low range, so basically close to minimum, and only few values are close to maximum. Most likely the master threads have higher values than the worker threads, and that is looks like that's the case. Okay, somehow the coloring is jumping. Okay, and then here we see that, for example, the execution of the iterations are pretty much homogeneous, and only in the center for iteration 3, 4, 5, 4, 3, 6, and so on, the timings are really going up. However, only for master threads, but not for some worker threads. The worker threads, they take most of the time similar values. That might be due to some specific domain decomposition, or maybe some boundary communication, or maybe even some noise in the system. So to take a closer look, so what's about this iteration, we have to actually go to the loop itself. So if we expand it, we don't see iterations because they have been aggregated. If we take a look at the in a context menu, we see that there is a show iteration menu is available. It means the iterations are recorded, are there, but they are hidden. So if we select show iteration, we see that the loop is actually expanded and every iteration is explicitly listed. And the bar plot is in this situation doesn't display any data, because if we select iteration 1, iteration 2, there is nothing to display as a bar plot, as a chart, so therefore there is no data to display. But we remembered iteration 3, 4, 5, that was more interesting, so there was some spike. And if we take a look, here we have the values around 0, 0, 7, and then if we go to 3, 4, 5, suddenly 1. So obviously there is something going on, and we can take a look, then closer look in the system tree. So if we take a look at the iteration 3, 4, 4, we see that the master threads are indeed 0.07 and then 0.04, 4, 4, and that's pretty much identical to MPI ranks. But if we go on 3, 4, 5 iteration, we see that the worker threads are staying the same, approximately 0.03 or 4, but the master thread takes suddenly longer to execute. So we can take a look what exactly takes longer. So we expand these iterations, and just we expand both of them, so just to compare. We see that the exclusive values are identical, so this execution doesn't change from iteration to iteration. Exchange Jacobi MPI data is approximately 0.2, 0.2 here, and here and here, so that is always in the same range. The parallel loop is approximately the same range, but if we take a look at all reduce, here we have 0.02, and here we have suddenly 0.329, 0.2, and here is again 0.02. So obviously for these two iterations, the all reduce suddenly took way more longer than previously. So if we take a look in iteration 3, 4, 4, we see that here is the timings are 0.002, 0.008, and so on. But in the longer execution, like here, suddenly it is 0.1, 0.1, 0.1. MPI rank is the minimal. If we take a look at the number of sent bytes, we see that the number of bytes is all the time the same. So it's not about we send larger piece of data, it's something different. What exactly it can be, this profile doesn't allow us to conclude, so we have to make another measurement, perhaps with tracing, maybe with perform multiple measurements if it is a system jitter. If these values are deterministic and reproducible, then one has to study why exactly for this iteration this MPI all reduce takes longer. As well, we have seen that somewhere by 4 here also we have larger values, and again we have the all reduce is larger. So that might be the influence of the system load, or might be some deterministic effects. So for that one has to perform further measurements. And that's pretty much it, what this plugin allows you to see. So again, if we hide the iteration, we basically aggregate them. So first we resolve them on a level of measurement, but then we aggregate them on a level of cube. And Barplot then allows you to visualize dynamic of the metric, in this case it's time, along the iterations. As well, we see that, for example, by the end of the loop, the last iterations, the minimal, the values are dropping. However, not the average and not the max. So it's obviously that some workload changes, probably some balancing effect or something. So again, one would have then to study this final part of the loop. Okay, and that's pretty much it. Summarizing it, as soon as you have loop, instrumented loop in your measurement, whether it is instrumented by Scorpy or you instrument it manually and then you assign manually, you tell the CubeGUI that this is a loop, then the Barplot plugin gets activated as well as heatmap, and then you can study dynamic of the performance data. I hope you understand how this plugin works, and it helps you then in the further in your future performance analysis. And at this place, give us a like, subscribe, and if any questions, then write a comment under this video. And see you next time. Bye bye.